Hey, welcome back, you guys. Let me take a look at the first derivative test, and let's talk about if a function is increasing or decreasing or constant. Technically speaking, if a function is increasing, if your x1 is less than x2, then f of x1 has to be less than f of x2 for all x1 and x2 on that interval. So in other words, you're going up and to the right. If a function's increasing, you're going up and to the right. Can you see down here on the graph? We're going up and to the right there in blue. And we're going up and to the right, and it continues going up and to the right in blue there, right? And so in this one, in this case, it's increasing, and you don't worry about the endpoints. You're increasing from this x value at -1 to that x value at 0. Union, we're also increasing from this x value at this 1, right? But again, we don't include the endpoint on. So just to infinity, right? And so that's where we're increasing on this graph. Let's go ahead and do where we're decreasing. If you're decreasing, then whenever x1 is less than x2, f of x1's got to be higher than f of x2 officially, right? So you're going down and to the right. So like this function's decreasing up until -1, decreasing up until -1. Again, the intervals are always open, right? We're naming them in terms of the x values here. We're decreasing there, and notice we're also decreasing from an x value of 0 up until an x value of 1 there in red. We're going down and to the right. Now this graph doesn't show any place where you're just constant, but let me give you that definition. If x1 is less than x2, f of x1 would be equal to f of x2. So for example, let's say you had a graph that decreased until 2, and then it went flat until 5, and then it increased again, right? This is the part where it would be constant. So in this case, it's constant from 2 to 5, right? So that's an example of a area where it's constant, interval in which it's constant. All right, let's go back and answer the rest of the questions on this one. Indicate all extremists, so our relative max, min, and absolute max, min. So if you look here on the graph, hopefully you can see that this point right there is 0, 0. We have a relative max, meaning in that area, that's the highest point, or a local max. Relative or local max of 0. It occurs at x being 0, right? So it's the y value is the relative max. And then if you notice over here, both of those are minimums, and they both hit at -1. So the relative or local min, let me do the as points of -1, -1. So the relative of -1, it occurs at an x value of -1, and it occurs at an x value of 1. Well, these are also absolute. This is actually the absolute min. They're not only local minimums, they're also absolute, meaning the lowest point on the entire domain, right? So with this one, we're able to read the graph, but let's suppose a graph's not given. So do we need to always have a graph in order to find the intervals where it's increasing or decreasing? And no, we don't. Because if you look at where a function is decreasing, let me do it for this one. You see how you're decreasing right here on that in that area? Well, if you've got a function that's decreasing, or maybe you've got a quadratic, right? It's decreasing if I was to take the derivative, which is the slope of the tangent line, anywhere on that area where it's decreasing, can you see how that slope would be negative? So if the derivative is negative on the interval, the function is decreasing on that interval, right? Whereas, look over here on the quadratic. Let me take a derivative on the part that's increasing. You see how f prime, the slope of the tangent, is going to be positive anywhere where it's increasing. And finally, if the derivative is 0, like right here at its relative minimum, absolute minimum, right, f prime would be 0, then it's constant right there. Well, this is not on an interval in this case. It's just at a point is where this is constant, right? But if f prime is 0. Okay? So f prime is less than 0 is decreasing, f prime is greater than 0, and f prime equals 0 would be constant. So what we're going to do to find the intervals without a graph is we're going to find the critical numbers. So, and that'll give us the testing interval. So where's the derivative equals 0? Where's the derivative undefined? And then determine the sign there on those intervals. Okay? So let's go ahead and take a look at this picture, and then we'll do an example here. So this is just showing us, hey, if f prime is 0, right, that's a critical number, or if it's undefined, there's f prime, right? There's some other spots where f prime is 0. These are all critical numbers. F prime is 0. These critical numbers. Right in here, notice f prime is positive, so it's increasing. F prime, again, is positive. It's increasing. F prime on that interval is positive. It's increasing, right? Over here, we got f prime, the slope of the tangents are negative, so you know it's decreasing. Any slope of the tangent in that area is going to be decreasing. And finally, any slope of a tangent in that area is less than 0, so it's decreasing on that interval, right? So that's a graphical look at this first derivative test. Let's see if we can't make sense of it with this basic function, x to the 4th minus 2x squared. So we've got this polynomial function. And first of all, we should say this is a polynomial, so it's continuous and it's differentiable, right, throughout its domain. But let's go ahead and let's write it down, and number 1, let's find our critical numbers. So find our critical numbers first. So let's take the derivative, 4x to the 3rd minus 4x. And then let's go ahead and take a 4x out. We got x squared minus 1. Let's keep factoring that. Okay, so here's f prime of x, right? So our critical numbers, where is this undefined? I have no place where it's undefined, right? It's not like I have a denominator or anything here on the derivative function. But where is it equals 0? Solve each of these. Divide by 4 both sides, so I have 0, 1, and negative 1. So what I'm going to do is now I'm going to go ahead and do, this is my first derivative test. So I'm going to say, all right, these are my critical numbers. Negative 1, 0, and 1. Okay. What is this graph doing to the left of negative 1? Right? Well, let's plug something in. Let's test it. So I'm going to go ahead and test like negative 2, something to the left of negative 1. So let's test it. So remember, f prime of x is 4x, x minus 1, x plus 1. I'm going to throw in negative 2. And so f prime of negative 2, I got negative 8 times negative 3 times negative 1. So it looks like I end up with negative 24. What's important? This is negative. Well, since it's negative, I know the function is the original function must be decreasing, right? The original function must be decreasing. So if you want to think about, graphically, I know we haven't done the graph on this, but this is an x to the fourth value. So it goes up and up. It has at most, it's a fourth degree. So from your pre-calculus, you have at most 3 turning points. And I hit, or I'm sorry, it's 0, 1, and -1. I don't know where. Oh, I'm sorry. This was originally, originally an x to the fourth. There it is. And at 0, 1, and -1, maybe it's something like this, but at 0, this derivative is 0. At -1, -1, the derivative is 0. F prime is 0, 0, and f prime at 1 is 0, right? So this is saying to the left of -1, all these slope of the tangent lines are negative. So the function must be decreasing up until -1. Now, again, I don't know what this graph exactly looks like right now, but we're going to continue on with this, so that's probably not a very good visual of that. But let's test something between -1 and 1, like about -1/2. So we'll plug that into the derivative. So I got 4, I should put -1/2, -1/2 minus 1, -1/2 plus 1. So I got 4 times -1/2, I got -2, -1/2 minus 1, I got -3/2, I got 1/2. Negative times a negative is a positive. All I care about is this is positive. So it's the function is increasing, positive. F prime is positive. So the original function is increasing between -1 and 0. The original function is increasing. Over here it was decreasing, right? Now I'm going to plug in like 1/2, something between 0 and 1, right? So I'll plug in 1/2. So I got 4 times 1/2, 1/2 minus 1, 1/2 plus 1. I got 2 times -1/2 times 3/2. A positive times a negative times a positive is a negative. So f prime of 1/2 is negative. The original function must be decreasing between 0 and 1. And I just like to put the little slash on there to remind myself that the original function is decreasing there, right? That's why I put the little, it's showing me that the slopes of the tangents are negative. So the original function decreases between there. All right, let's plug in like 2 now. Again, we're testing it into the original function. So f prime at 2. So I got 4 times 2. I got 2 minus 1. I got 2 plus 1. I got 8 times 1 times 3. This is definitely positive. And so that means it's increasing after that. Okay, so let's go ahead and sum this up because it's asking us where is it increasing and decreasing. So step 3, here's our summary. Where are we increasing? Well, we're increasing in this area and that area, right? From -1 to 0 and 1 on. Where are we decreasing? Now I'm looking, I'm decreasing in here, and I'm decreasing in there. So -∞ up to -1, and 0 to 1. How about local or relative min and max? So just messed that up. I don't know if I said that right and wrote it wrong, but I screwed that up. Are increasing from -1 to 0 and 1 on. I'm not sure if I said that right there. All right, now on to our relative mins and maxes. Well, if the function decreases, right, the function decreases to 0, then it increases, and then it decreases again, and then it increases, right? So you see how we would have a relative minimum at those 2 points right there? So we decrease, so relative min here, relative min there. Okay, so relative min at x being -1 and x being 1. And so then I would throw it into the original function. Okay, the original function. Remember, we're trying to find the original function. So x to the 4th minus 2x squared. Plug in the -1, so I got -1 to the 4th minus 2 times -1 squared. So I got 1 minus 2. It looks like I got -1. Plug in the 1, and I got -1. Plug that into the original. Okay, so that's a relative min. Which in this case ends up being, as I know it goes up to the left, up to the right, those are actually also absolute minimums. All right, how about local maximum? Well, it looks like it's only right here where it's at an x value of 0, it increases and then it'll decrease, right? So it'll have a relative max right there. Relative max at an x value of 0. And again, plug it into the original function to find what the relative maximum is. So you throw the 0 in, and it ends up being 0, right? So, in fact, let's draw a little more accurate depiction of this graph. It's an x to the 4th, positive 1x to the 4th. So it's kind of like x squared goes up and up. I know it hits at -1, -1. I know it hits at 0, 0, and I know it hits at 1, -1. And it decreases until there. This is a polynomial, so smooth and continuous. Then it's going to increase between -1 and 0. Then it decreases, and then finally it's going to increase. So that's kind of a decent little picture of that thing with the information that we have. All right, let's take a look here at this f of t. We've got a -t cubed plus 27t. Okay, and we're going to run that first derivative test to see where it's increasing, decreasing. I'm going to take a -3 out, so I'd have t squared minus 27. Oh, t squared, my goodness, minus 9. There's our f prime of t. So number one, our critical numbers is what we're finding here. Where's our derivative? Undefined, nowhere, but where's our derivative equals 0? T being 3, t being -3. So let's throw it on our first derivative test, -3 and 3. And let's test to the left of -3. So f prime, here's our f prime, t minus 3, t plus 3. Let's throw in -4. Negative times a negative times a negative is a negative. So this thing is decreasing until -3, right? So we're decreasing. Let's throw in 0. F prime at 0. So I have -3, 0 minus 3, 0 plus 3, -3 times -3 times positive 3 equals, that's a positive 27. So then we increase. And now let's throw in 4. Let's throw in 4, and I get -3 times a positive times a positive. So that'll be negative once I throw it in. So we know it decreases if I plug in a 4 into the first derivative. Right? So let's go ahead and summarize this, looking at our first derivative. So where are we increasing? It's like just on the interval between -3 and 3 is the only spot that we're increasing. Where are we decreasing? From negative infinity up to negative 3 and 3 on to infinity. All right, how about where are our relative local, both local and absolute? We'll address both of those. So let's talk about, we have a potential local here. If I decrease and then increase at negative 3, would be a local or relative min at that negative 3 value. And then I would have a relative or local max. Oops. If I increase and then decrease, right, the max would be, local max would be at 3. Now I want to plug these into the original function. Remember, the original function was f of t equals negative t cubed plus 27t. So let's plug the negative 3 in first. I got negative 3 cubed plus 27 times negative 3. I got negative 27 times 3, 71. Oh, that's not, yeah, sorry. That's 81, my gosh. There we go. So I got 27 minus 81, and negative 54. Plug the 3 in. I got negative 27 plus 27 times 3. So I got a positive 54 there. Now let's discuss, get a little room here for the graph. Kind of think about this graph. I know it doesn't ask you to graph, but the original function was this negative t cubed plus 27t. So the degree is odd, but the leading coefficient is negative. So instead of being like x cubed, it would flip that around and be more like negative x cubed, right? So it goes up to the left as far as end behavior, down to the right. That's how this thing will behave. And then at negative, it'll come clear down to negative 3, negative 54. So it'll come clear down to this negative 3, negative 54. And remember, it's decreasing up until then, right? So it's decreasing to there. And then it'll increase clear up until 354. So go way up to the 354. And then it's got to drop way back down. Okay. So since it's going way up to the left and way down to the right, there's no absolute maximum or minimum. There is no highest point and there is no lowest point. So these are only local minimums and a local or relative maximum. All right, let's get into, how about transcendental? Here we go. How about this one, x minus 2 times e to the negative 3x. So I'd go ahead and run my product rule when I'm finding my critical points here as I take the derivative. All right, so here's my function. So the derivative would be derivative of the first. So derivative of x minus 2 is 1. Derivative of the first times the second plus the first. Derivative of the second. Derivative of e to the negative 3x is ln of e. E to the negative 3x, derivative of negative 3 is negative 3. Derivative of negative 3x is negative 3. So we got e to the negative 3x, and ln of e is just 1. So I got, is that minus 3e to the negative 3x times x minus 2. So let me take a e to the negative 3x out of both of those. I'd be left with 1 minus 3 and x minus 2. I factored out an e to the negative 3x there. So I got 1 minus 3x plus 2. I'm sorry, 1 minus 3x plus 6. So 1 plus 6, I got 7 minus 3x. And there's our derivative, f prime of x. Right? So where's this thing undefined? Nowhere. But how about where's the derivative 0? So I'd say, well, e to the negative 3x, where's that equals 0? 7 minus 3x, where's that equals 0? Add 3x to both sides, so it looks like x would be 7/3 once I divide by 3. That's one of my critical points. Now how about this one over here? Well, let's undo it with the natural log. And so we have negative 3x. Oh, we can't take the natural log of 0, right? That's not defined. Remember the natural log, here's the natural log of x. Remember, x got to be positive, right? It's got a vertical asymptote, x equals 0. So there is no natural log of 0. If you punch that into your calculator, it'll undefine it. Or it's a garbage calculator, better throw it away. So let's go with f prime is 7/3. So we're doing the test now. F prime test, so 7/3. So let's plug in something to the left of 7/3, and we're plugging it into our derivative here, e to the negative 3x, 7 minus 3x. Again, this is the first derivative test. So like, let's plug in, I don't know, how about 2? 7/3 is just to the left of 2, right? 6/3 is less than 7/3 there. So e to the negative 3 times 2 over 7 minus 3 times 2. That's 1 over e to the 6 times 7 minus 6 is 1. Well, e to the 6 is positive, so this is 1 over e to the 6. So that's positive. That's all we care about, is it positive or negative. It's positive, so the original function is increasing up until 7/3. And then let's pick something to the right of 7/3. About 3, f prime at 3. So we got e to the negative 3 times 3, 7 minus 3 times 3. So e to the negative 9, 7 minus 9. So I got 1 over e to the 9th times the negative 2. So I got negative 2 over this e to the 9th. Remember, e to the 9th is a positive number. So a negative over a positive is a negative. So the original function is decreasing after 7/3. So let's go ahead and summarize this. So the function increases negative infinity up to that 7/3, and the function is decreasing. The original function decreases after 7/3. Okay, so we'll have a local max, because it increases then it decreases, at that 7/3 point. At whatever 7/3 comma whatever, right? So I'd have to plug that in. Where's my original at? X minus 2 times e to the negative 3x. So I throw the 7/3 again. This is into the original function, right? I'm trying to find local max min of the original function. So I got 7/3 minus 6/3 is 1/3. E to the negative 21 of e to the negative 7. So I got 1 over 3 e to the 7th. Whatever that value is, right? All right, let's take a look at this one here. We got square root of 9 minus x squared over x squared. And, you know, before I even start this, I kind of want you to think about your domain on this. Your radicand, this 9 minus x squared, remember this got to be greater than or equal to 0, right? So if I add x squared, I'm just finding my domain. Think about this before you start this. So x squared less than or equal to 9. If I square root this, now I have an inequality, so I'm going to be proper about that. That's the absolute value, which means I'm between 3 and negative 3. But look at the original function. I can't be 0 either, right? But I can't be 0. So this domain, I'm between 3 and negative 3, but I can't be 0, right? And so now let's go ahead and think about, let's take this derivative now. And this is my domain. Let's find a critical point. So f prime of x, I have derivative of the top, 1/2 9 minus x squared to the negative 1/2 times derivative of the inside, negative 2x. Derivative of the top times the bottom minus the top. Derivative of the bottom, well, that's 2x, and this is all over bottom squared. And so this derivative, see how these 2's cancel right there? I got negative x cubed over this square root of 9 minus x squared minus 2x square root of 9 minus x squared. This is all over x to the 4th. And so I'm going to get a common denominator. You know, this is over 1. So let's give it a square root of 9 minus x squared. Top and bottom here. And so this f prime of x ends up being negative x cubed minus 2x, and square root times square root just undoes the radical. This is all over, I got x to the 4th in this common denominator now. Let me distribute that. I got negative x cubed minus 18x plus 2x cubed. This is over f prime of x. So f prime of x. Oops. 2x cubed minus x cubed. I get x cubed minus 18x. X to the 4th square root of 9 minus x squared. You see how I can factor out an x out of each of those on the top? And I could factor an x out, I'd have that. So one of those x's cancels, leaves you with x to the 3rd. So this ends up being f prime of x, x squared minus 18 over x to the 3rd, square root of 9 minus x squared. Okay, so what are our critical points? Well, where's the derivative equals 0? Well, if the numerator is equal to 0, that'll be true because 0 over anything is 0. So I add 18, square root, so x is plus or minus the square root of 18. In other words, plus or minus 3 root 2. Okay. Well, if you think about that, square root of 18 is 4 point something, right? Square root of 16 is 4. This is 4 point something. So this is actually outside our domain. So there's no need to test this because it's outside our original domain. Where is f prime undefined? Well, if you notice x cubed is 0, x being 0, or wherever the square root of 9 minus x squared is 0. Here I'd square both sides. Plus or minus 3. Okay, so 0 plus or minus 3. And if you remember our domain, that's the end of our domain. So when we do this f prime test, I'm cutting it off negative 3 to 3. I know f prime is undefined, but I'm still going to test around it. Okay, I'm going to test around it. And why am I going to test around it? Because when x is 0, what I have is I have a vertical asymptote right there, right? It's not defined there anyways. So I still want to test around it. Maybe it's increasing up to that vertical asymptote, or maybe it's decreasing up to there. I still want to test around it, even though it's not officially a critical point, because it's not defined at 0. The original function is not defined at 0. And then, like I said, don't test. No test out here. I'm not in my domain. No test out here either. So I'm just testing to the left and negative 1. So like maybe to the left of 0, like negative 1. And over here, like maybe 1. Okay. I'm going to put that into my derivative. So here's my derivative. We got f prime of x equals x squared minus 18 over x cubed square root of 9 minus x squared. Let's plug in negative 1 squared minus 18 over negative 1 cubed square root of 9 minus negative 1 squared. So we got 1 minus 18, negative 17 over negative 1, and then 9 minus 1 square root of 8. Well, I got negative over a negative, which is a positive number. So this original function increases from negative 3 up to 0. Now let's throw in 1. I got a negative, and these are positive. So a negative over positive is a negative. So the function then decreases. So let's summarize this. I'm increasing from negative 3 to 0. Remember, these are always open intervals. And I'm decreasing from 0 to 3. Okay. Now, there's no absolute max or relative max. No sort of max at x being 0, since there was a vertical asymptote at x being 0. Remember, the original function is not defined there at x equals 0. So even though it increases up to there and then decreases after that, it still doesn't have a maximum there. All right, let's take a look at this trig function now. How about sine theta, cosine theta? Let's find all our extrema on this one. So here's our function. And notice it says, but only on, we're cutting this domain off, only from 0 to pi. Are we worried about it? So let's find our critical points. Let's take the first derivative. Derivative of the sine is the cosine. So derivative of the first times the second plus the first. Derivative of the cosine, derivative of the second is negative sine. So we got cosine squared theta minus sine squared theta. So what I'm going to do is I'm going to use the old Pythagorean identity. Remember, sine squared plus cosine squared is 1, right? And I'm going to replace the sine squared. So sine squared would be 1 minus cosine squared. I need to either get them all into cosines or all of them into sines. But I'll go ahead and replace the sine squared. So we have cosine squared minus 1 minus cosine squared. And so we've got cosine squared theta minus 1 plus cosine squared theta. So it looks like we got two of these cosine squared thetas minus 1. That's our f prime of theta. Okay. So in other words, if I was to let this be 0, add 1, divide by 2, I got cosine squared theta equals a half, square root. Where's the cosine of theta? Plus or minus, the square root of 1 is 1, square root of 2 is square root of 2. Rationalize that. All right, where's the cosine of theta plus or minus root 2 over 2? So now you're looking on your unit circle. You're like, where's the cosine root 2 over 2? Well, there and there, right? So this is going to be pi fourths. I know theta could be pi fourths. The other one is 7 pi fourths. But remember, we're only looking between 0 and pi. So we don't care about the 7 pi fourths. Where's the cosine negative root 2 over 2? So over here on your unit circle, and here on your unit circle, right? So that would be at 3 pi fourths and 5 pi fourths. Well, that one's also not in your domain. We're only looking from 0 to pi. Okay. So let me erase this. Let's put our first derivative test now. Let's do our with our critical points of pi fourths and 7 pi fourths. So here's our f prime. Remember, we're only looking between 0 and pi. But our critical points were pi fourths and 3 pi fourths were our two critical points that we were looking at. So if you're plugging in, let's see, where's our derivative? Let's plug in something before pi force, like pi 6, right? So f prime of theta is 2 cosine squared theta minus 1. Plug in pi 6. So I got 2 cosine of pi 6 is squared minus 1. Cosine of pi 6 is root 3 over 2. So I got 2 times 3/4 minus 1. I got 6/4 or 3/2 minus 1. So I got 3/2, so I got 1/2. So this is positive. So the original function increases from that 0 up to pi 4. So again, the 0 and the pi is just the domain. They cut this domain off for us. Plug in like pi, or I'm sorry, something between pi force. I can't plug in pi force and 3 pi force. How about like pi thirds? So you got 2 cosine of pi thirds. Cosine of pi thirds is 1/2. I got 2 times 1/4 minus 1. I got 1/2 minus 1. So it looks like we're negative. So we decrease between those two. And then I'll put in something between 3 pi fourths and pi. So 5 pi 6, that would work. I punch in 2 cosine of 5 pi 6 is negative root 3 over 2. Square that, minus 1. That'll end up being positive for you. And so it'll increase. So let's go ahead and write this out here. Let's see. Let me erase some of this. Get myself a little room. So we're increasing 0 up to pi fourths, and then again from 3 pi fourths on up to the, keep going up to the pi. Remember, we cut this off. We're decreasing in between pi fourths to 3 pi fourths because the derivative is negative. That means all the slope of the tangents are negative. That means the function is decreasing, right? And so we would have a relative max at pi fourths whatever. And then we'd have a relative min at that 3 pi fourths, right? Because it goes down and then goes back up at 3 pi fourths. And we'll go ahead and let's punch those in. So let's see, the original function was sine cosine. F of theta equals sine cosine. So let's go ahead and punch in pi fourths. You got sine of pi fourths, cosine of pi fourths. Well, that's root 2 over 2. That's root 2 over 2. Looks like I got 2 over 4, which is 1/2. Punch in 3 pi fourths. So I could get negative 1/2 because your cosine there is negative root 2 over 2. All right, last one here. I would go ahead and before I even do anything, I'm going to write this in a form that 2/3 plus x to the 2/3 times x to the 1 is x to the 5/3. Put it in a form where I can just run the power rule. Minus 12x to the 2/3. Okay, and then let's go ahead and take its derivative. So I got 3, I got 5/3. X to 5/3 minus 1, so 2/3 minus 12. I got 2/3. X to the 2/3 minus 1 is negative 1/3. So it looks like I got 5x to the 2/3 minus 24 over 3, so minus 8 over that x to the 1/3. Okay, so let me write it this way, or let me get a common denominator. So times x to the 1/3, x to the 1/3. So this is 5, x to the 2/3, x to the 1/3 is x to the 1. So 5x minus 8 over x to the 1/3. Okay, and so our critical points would be, where's this thing? Where's f prime equals 0? Well, if the numerator is 0, that'll be f prime equaling to 0. So 8/5. All right, and of course I would show it into the original and make sure it satisfies the original, and it does. So it is a critical point that is defined in the original. Where is f prime undefined? Well, anywhere where x to the 1/3 equals 0. Cube both sides, and I have x being 0. So then let's go ahead and run our f prime test from 0 to 8/5 here. And so I throw in maybe -1. Maybe I throw in a 1. Here's my derivative. Let me go ahead and write my derivative before I choose that last one. 5x minus 8 all over to the 3rd root of x, or x to the 1/3. All right, let's throw in the -1. -5 minus 8, I get -13. 3rd root of -1 is -1. So negative over negative, that's a positive, so it'll be increasing. Let's throw in 1 now. So I got 5 times 1 minus 8 over the 3rd root of 1. I got -3 over 1. That's a negative, so that thing will be decreasing. So I'm going to be strategic and pick 8 here. I'll pick something just to the right of 8/5, and that's because I know the 3rd root of 8. So f prime at 8, I got 5 times 8 minus 8 over to the 3rd root of 8. So I got 40 minus 8, 32 over 2. So this is positive. So it looks like I increase after that. Okay, let's go ahead and summarize this. So step 1 was to find our critical points. Step 2 is take the first derivative. Let's go ahead and summarize this. We are increasing from -infinity up to 0, and then again from 8/5 on. 8/5 on. We're decreasing between them from 0 to 8/5 because the derivative is negative. Our local max, it increases, then it decreases. So at 0, I would have a local max, and I'd have a local min at 8/5. So I plug those into the original function. So here's the original 3x to the 5/3 minus 12x to the 2/3. That's the one I'm plugging it in. So that'll give you 0. Oh, what does the 8/5 give you? Plug that in. 3 times 8/5 to the 5/3 minus 12, 8/5 to the 2/3. Or I guess I could plug it into the original. Here's the, before I distribute it, 3x to the 2/3, x minus 4. I could throw that 8/5 in there. Yeah, either of those, and that'll spit out come on. That's 8/5 to the 2/3, or in other words, right there. All right. Thanks for watching. I hope that helps. See you next time.